Today we discuss about closed graph theorem on important topics of functional analysis. First we start about closed mapping. Okay, to start closed mapping, let xy be two topological space. Let xy be two topological space. And tx to y be a mapping. Then T is closed if T is closed if TC is closed TC is closed for each closed set C in X. Each closed set C in X. Okay. Now we're going to graph of a mapping. Closed set. Now we're going to graph of a mapping. Okay. Let xy be two set. Let xy be two sets. And let t dt to y. Let t dt to y be a mapping. Then the graph of t. Then the graph of t is denoted is defined by gt equal to x dx where x belongs to dt, subset of x Cartesian product y. Okay, then gt is the graph of t. Now observation is that x Cartesian product y are linear spaces and gt subset of x Cartesian product y, and gt is a subspace of gt be a subspace of x Cartesian product y. Okay, now we're going to one definition. Let xy be two norm space. Let xy be two norm space. Let xy norm spaces and t dt subset of x to y be a mapping. Then t is said to be closed. Then t is said to be closed if graph of t is closed. If graph of t is closed. Okay, now how we do it? Xn be a sequence in dt, xn tends to x and txn tends to y, then tx equal to y. Okay, now we start the closed graph theorem. Statement of this closed graph theorem. We erase this portion. Now theorem, closed graph theorem. Let x and y be Banach spaces. Let x norm x and y norm y be Banach spaces. And let t dt subset, let t dt subset of x to y be a linear mapping, be a linear mapping such that dt and gt are closed, such that dt and gt are closed. Okay, then t is bounded, then t is bounded. Now we're going to prove of this problem. This theorem we proved now. Now define norm of xy. This x Cartesian product y equal to norm of x plus norm of y. For all xy belongs to x Cartesian product y, then x Cartesian product y norm of x Cartesian product y be a Banach space. Okay, now define p gt to dt such that, or by px dx equal to x for all x belongs to dt. We now show that p be linear 1 1 on 2 and bounded. Okay, now start about that first linearity. Let x dx y dy belongs to gt and alpha belongs to k. Then p of x dx plus y dy equal to p of x plus y tx plus y equal to x plus y equal to p of x dx plus p of y dy. Again p of alpha x dx equal to p of alpha x and alpha tx. Then this one equal to alpha x, this one equal to alpha p of x dx. Okay, then we write that p be linear. Okay, now we erase all portions and going to further p be 1 1. Now we're going to 1 1. P 1 1, we have to prove that. Now we write x dx belongs to gt for some x belongs to dt, and now p of x dx equal to 0 implies that x equal to 0. So car p equal to 0. So p is 1 1. Now on to let x belongs to dt. Let x belongs to dt. Then we find x dx belongs to gt such that px dx equal to x. So p is on 2. Next, boundedness of p. Then boundedness of p, norm of p, x dx x equal to norm of x less than equal to norm of x, norm of dx. This equal to norm of x dx. Okay, x Cartesian product y. For all x dx belongs to g. For all x dx belongs to gt. Then clearly p norm p less than equal to 1. Norm p less than equal to 1. So p bounded. Then p is 1 1 onto bounded linear operator from Banach space onto a Banach space. Then clearly p is 1 1 onto bounded linear operator from a Banach space to from a Banach space gt norm x Cartesian product y onto a Banach space dt norm x, because gt and gt are closed, because dt gt are closed. Hence, by Banach bounded inverse theorem. Hence, by Banach bounded inverse theorem. Hence, by Banach bounded inverse theorem, P inverse dt to gt exists. P inverse dt to gt exists. and continuous and continuous. The, or continuous means linear and bounded. Okay, then then we write P inverse equal to P inverse of x equal to x dx. Okay, for all x belongs to dt. Now boundedness of t. Now we prove boundedness of t. Where is the lower portion? Next, norm of tx y less than equal to norm of xx norm of txy equal to norm of x dx x Cartesian product y equal to p inverse x, okay, x Cartesian product y less than equal to norm of p inverse norm of x, here x. This implies that norm of t less than equal to norm of p inverse less than equal to 1, hence norm of t, hence t is less than equal to 1, so t is bounded. Okay, then we prove also that t is bounded. Now we discuss next thing. We prove closed graph theorem. Okay, now also we discuss some corollary. Okay, corollary about this closed graph theorem. We erase this portion and then we're going to some corollary. Okay, then we're going to some corollary. First, let x norm x and y norm y be Banach spaces. Be Banach spaces. And let t dt subset of x to y be a linear operator such that dt is closed. Be a linear operator such that dt is closed and t is bounded and t is bounded, then t is closed, then t is closed. Now let xn be a sequence in dt. Proof. Let xn be a sequence in dt such that xn tending to x, such that xn tending to x and txn tending to y for some x belongs to x and y belongs to y. We have to show that x belongs to dt and tx equal to y. Since xn in dt, with xn converts to x, and dt is closed, so x belongs to dt. By continuity of t, okay, txn converts to tx. Also txn converts to y, hence tx equal to y. So txn converts to this y, hence t is closed, hence x belongs to dt and tx equal to y, therefore t is closed. Okay, now we're going to another corollary of closed graph theorem. Now this one also a corollary. Okay, we first write this statement of this corollary. Let x norm x and y norm y be two norm spaces with y complete. Okay, be two Banach spaces, and t dt subset of x to y be a linear operator, be a bounded linear operator such that gt is closed, then dt is closed, okay. How we do this? We do this so simply. First we start with one sequence. Okay, let xn be a sequence in dt xn be a sequence in dt such that xn tending to x such that xn tending to x for some x belongs to x, for some x belongs to x. We now show that we now show that x belongs to dt. Since xn convergent, since xn convergent, it follows that xn Cauchy. It follows that xn Cauchy. Now note that norm of txn minus norm of txn equal to norm of txn minus xn less than equal to norm t norm of xn minus xn tends to 0 as nm tending to infinity. Hence txn is Cauchy. Hence txn is Cauchy. And txn tending to y and txn tending to y for some y belongs to y. And since y is complete, since y be complete, since xn tending to x and txn tending to y, txn tending to y for some x belongs to x, and y belongs to y, and t is closed, and t be closed, then x belongs to dt and tx equal to y. So dt be closed. Okay, so we going to this corollary. We first start about some definition, closed mapping, graph of mapping, and then definition of when graph closed, then t is closed, and then closed graph theorem, and two corresponding corollary of closed graph theorem. Okay, now we discuss one example. Okay, one example, then we stop. We erase whole portion now, then we write example or understand this one. Example, first let xy equal to c01. Okay, be a Banach space with norm infinity. Be Banach space with norm infinity. Set c equal to if such that c01 2 are such that if test is continuous. Define tc2y by tx equal to x dash. for all x belongs to C. Okay. Then T is linear, T is 1 1, T is closed, T is unbounded, T inverse is bounded. Now we first show that T is closed. Okay, T be closed. How we do this? Let Fn be a sequence in D such that Fn tending to F. Let Fn be a sequence in D. Let Fn be a sequence in D such that Fn tending to F, such that Fn tending to F, and Tfn tending to Z. For some F belongs to X, for some F belongs to X, and G belongs to Y. We have to show that F belongs to D and Tf equal to G equal to F dash. Now for x belongs to 0 1, for x belongs to 0 1, integration of 0 to x gt dt equal to 0 to x limit n tending to infinity t of fn t dt. Okay, then this equal to 0 to x fn dash t limit n tending to infinity dt. This equal to limit n tending to infinity 0 to x fn dash t dt. This equal to limit n tending to infinity fn x minus fn 0. This equal to fx minus f0. Okay. Then f dash x equal to gx. F dash x equal to gx for all x belongs to 0 1. Since f0 equal to 0, okay, then we show that therefore f belongs to dt and tf equal to f dash equal to g. So hence t is closed. Hence t is closed. Okay. Now we're going to next portion. T inverse is bounded. Okay. Then we use this portion. Now T inverse is bounded. T inverse be bounded. Now T inverse RT to D. T inverse RT to dt by or T inverse RT to D exists since T is 1 1, exists since T 1 1. Okay. Now T inverse RT to D, where D equal to F belongs to C01, such that F dash belongs to C01 and F of 0 equal to 0. Okay, then G belongs to D. Now GU equal to 0 to U G dash T dt, less than equal to 0 to U G dash T dt, less than equal to 0 to U G dash infinity dt, less than equal to G dash infinity. Okay, U belongs to 0 1. Now taking supremum with respect to U, hence norm of G infinity less than equal to norm of G dash infinity. Now with G equal to F, put G equal to F, then this implies that norm of F infinity less than equal to norm of Tf infinity. Okay, so this shows that norm of T greater than equal to 1, and also T inverse y equal to norm of T inverse y infinity less than equal to norm of y infinity. This implies for all y belongs to RT. This implies that norm of T inverse less than equal to 1. Hence T inverse is bounded. So T inverse be bounded. Okay, but T is not bounded here. So today we stop here.